For centuries, we have treated electricity and magnetism as separate forces, invisible fields shaping our world. But hidden beneath these natural phenomena lie a unified truth, a mathematical truth, waiting to be realized in the physical world. The universe is boiling with electromagnetic radiation, from radio waves to gamma rays, and it is the mathematics that binds the abstract world into the concrete realm of the physical universe. Many mathematical pioneers paved the way for our understanding behind the magic that is electromagnetism. From Carl Friedrich Gauss measuring the Earth's magnetic field, developing his divergence theorem, among other accomplishments, including his theory of surfaces which led to differential geometry. Gauss's theorem lends itself to a very important piece of electromagnetism. And then, of course, there's George Green, scratching away equations in his dusty notebook in obscurity, and George Gabriel Stokes, pondering fluid flow. All of these mathematicians provided a basis for James Clerk Maxwell to unify electricity and magnetism into the theory of electromagnetism. And today's video will talk just about where those equations came from and how it revolutionized our world. (1820) Hans Christian Ørsted. While experimenting with electrical wire in a battery, with a current running through the wire, he noticed that when he placed a compass needle near the wire, with electrical current running through it, it would influence the needle of the compass, which is typically only influenced by a magnetic field. So when the circuit was on and electricity was flowing, the needle moved in a specific direction, according to the magnetic field flow. And when he switched the direction of the polarity of the battery, meaning sending the current in the opposite direction, he noticed the needle would point in the opposite direction. This was the first link between electricity and magnetism. (1820 to 1825). André-Marie Ampère. Ampère, whose law is named after him, is responsible for describing the nature of current. Like water flowing down a stream, charges flow down a wire, and how fast they move down the wire, the rate of change of the charge, is known as current. 1831. Michael Faraday, moving a magnet through a coil of wire, notices that it induces an electrical current. And by 1861 to 1865, James Clerk Maxwell put it all together in his unified theory of electromagnetism, which predicted electromagnetic waves traveling through space, just like light. In fact, he was the one who predicted that light is an electromagnetic wave. And that caught the attention of some most prominent physicists. In fact, it would be Albert Einstein who would say, "I do not stand on the shoulders of Newton. I stand on the shoulders of Maxwell." James Clerk Maxwell's theory of electromagnetism was the key pinnacle point that set the Industrial Revolution forward. He lit the world with an understanding of how to take mathematics and bring it unified into the physical realm. Let's begin with our first insight into electromagnetic theory, with one that lies at the heart of calculus, the fundamental theorem of calculus. This statement says that summing up all the small changes, the derivatives, over the one-dimensional line segment given by the interval AB is equivalent to taking the total change evaluated on the boundary of the interval, which are just zero-dimensional points AB. We will see that this is Stokes' theorem in one dimension. The tools of calculus, vector calculus that is, start with the components of the gradient of a scalar field. The gradient of a field, lowercase f, a scalar field, is a vector field. Then, if we have a vector field given by capital F, we can define the curl of the vector field, and it is a differential operator that encapsulates the tangential circulation of the field. We can also define the divergence of the vector field, and it corresponds to the normal component of change, the outward flow of a surface. Consider a metal plate that's been sitting out in the sun, so parts of it are hot and parts of it are cold. Cold being indicated by the blue sections, hot being indicated by the red sections, and you can see the flow of temperature given by the gradient in the picture. That word gradient is used in color for a very specific reason, directly connected to the gradient of the field that we're about to put on this scalar field. So by finding the gradient of the scalar field, we overlay it with a vector field, at each point assigning a vector. That vector points in the direction of greatest increase. So now we can ask the question, what happens if we take a path through this metal plate? Let's say you're an ant on this metal plate and you travel from, let's say, a point A to point B along some curve C. one could ask what is the total change in temperature as one traverses along this path. And this idea along a plane will naturally be taken to higher dimensions when we talk about a surface. And the key part here is understanding the concept of a line integral. So if one induces a gradient vector field on top of a scalar field, grad f, then at each point, xy, a vector, which is given by an arrow, is assigned pointing in the direction of the greatest increase, having a magnitude proportional to the temperature or the scalar value at that point. And vectors point from cold to hot, which is often why a negative sign is introduced due to the fact that temperature actually moves from hot to cold. So the gradient always points in the direction of greatest increase. A parametrized path on an interval AB, parametrized by the parameter t, is mapped into R3, a path, a three-dimensional path. The total accumulated change is given by the line integral. So in R2, we have a path on a two-dimensional plane. And the scalar field or vector field must have a domain that contains the image of your path. Now, a line integral or a path integral are the same thing, and we'll see that they have a very big influence in the idea of a vector field and taking a path through that vector field. This will become an important concept in the study of electromagnetism. Let's let dl be a small length along our path. Then the line integral is given by the integral of f, our scalar field, dl, our small little element of line, and that's going to be equal to the integral from a to b of the parametrized path inputted into our function multiplied by the length of the tangent vector dt. So in R2, let's consider a vector field, capital F, given in this notation with the I and j basis vectors, or sometimes given with the pointy vector notation, which is sometimes used to indicate an inner product. If we travel a path through this vector field, we will be influenced by this vector field. The path integral of f dl along this path is given by the integral from a to b of f of x of t times the tangent vector x prime of t dt. And this can be reformulated into the scalar integral, where we have the scalar product of our vector field f with the normalized tangent vector t. And the result is a one form that we are integrating over. So a path through a vector field is a little different than a path through a scalar field, and it is defined in this following way, where mdx plus ndy is a differential one form, something I mentioned in my previous video. This idea can then be extended into 3 and higher dimensions. Time to do some work. What is the work done in moving an object from point A to B? Well, it is exactly the line integral of the force field along the path in which the motion is implied. Newton's second law, for instance, is F equals ma. but can be rewritten as m dv dt. So with some notational gymnastics, we can conclude that the work done by a force field, F, is the change in kinetic energy. Thanks, Newton. Now, what happens if I travel the path in a closed loop? We get Green's theorem in 2 dimensions. The closed loop integral of our line integral, f dl, is given by the surface integral of the region it encloses, d. And it is really just saying that the sum of all the small circulations at all the points inside the enclosed region is equal to the total circulation on the outside of the boundary of the enclosed region. And so those circulations are given by dn dx minus dm dy. And that might look familiar to you if you're familiar with the curl of a vector field in 3 dimensions. So since we're working in 2 dimensions, we'll let the 3rd dimensional component be 0 in our vector field, and we will calculate the curl of the vector field to be just that, dn dx minus dm dy, along the kth direction. But since k dotted with itself is 1, we can write the surface integral as the curl of the vector field dot the k vector dA, where dA is dx dy, or the area element. This is Green's theorem of circulation in 2 dimensions. Now, in electromagnetic theory, E is the electric field and B stands for the magnetic vector field. So the expressions of the circulation of these fields, given by the curl of E and the curl of B, really describe what happens when you circulate those vector fields, especially through a wire. So now extending the idea of circulation into R3, into 3 dimensions, we have to consider surfaces living in 3 dimensions. A closed surface and the circulation of a vector field through that surface. Now we define a vector field with the functions m, n, and p in the I, j, k directions. And a normal vector is the cross product of the unit tangent vectors in the uv direction, where the uv directions are given by the parametrized surface directions. So we have an outward pointing unit normal defined on our surface. The closed path integral is equal to the surface integral of the circulation, or the curl, dotted with the normal vector, unit normal outward vector, ds, where ds is a surface component, and c is the boundary of our surface. The curl of f is a local operator. The integral over the boundary is a global one. So taking a closed curve C, and we calculate the flow of a vector field, this time across the curve, not along it, we get the outward flux or flow of the vector field across the curve C, equivalent to the, well, let's write it out here, the surface integral of the f dot n ds is equal to the volume integral of the divergence, Gauss's divergence theorem. So it's relating a surface integral to a volume integral, the accumulation of flow. When we talk about the divergence of an electric field, we're talking about the electric field generated by some enclosed charge. But since there is no such thing as a magnetic charge or a magnetic monopole, the divergence of a magnetic field is zero. We'll talk a little bit more about that later. Conservative force fields. In the world of physics, it is known that some forces are conservative. But what does that mean? What does it mean for a vector field to be conservative? Well, due to symmetry in nature, we find that some quantities are conserved, such as charge. And conservative forces have some very special properties. We'll talk about them now. Suppose our vector field F is a continuous one, such that it is the gradient of some scalar field, lowercase f. And when I say it's a function of class C1, I mean that it is differentiable. If this is the case, F is often referred to as the scalar potential of the vector field F. And it implies that the vector field F has path-independent line integrals. If the curl of a vector field vanishes, and by vanishes I mean it equals zero, then we say that the vector field is irrotational. And if F is irrotational, then F can be expressed as the gradient of some scalar potential field. The potential is often denoted as V in the world of electrodynamics, and it is so customary to say that a negative sign is assigned to that given the nature of what we talked about earlier with temperature. Potentials. Now for potentials, the following hold true. The curl of the vector field is zero. The path integral is path independent. It doesn't rely on the path. The closed loop integral is zero. And F can be written as the gradient of some potential scalar field, typically referred to as the potential field. Now, if the divergence of the vector field is zero, then we can make the assumption that F is the curl of some vector potential. The vector potential sometimes is assigned the letter A. So all of these conclusions about conservative systems stem from vector calculus formulas which encompass the del or nabla operator, the differential operator. The curl of a gradient is always zero, and the divergence of a curl is always zero. And these things have very real ramifications in the physical world when we apply these theories to electricity and magnetism. ElectroMagnetism. E is the electric field, B is the magnetic field. Two of Maxwell's equations describe the creation of these fields, and two of them describe how they change in time. The divergence theorem, the double integral, the surface integral of f dot n ds is equal to the volume integral of the divergence dv. If we let f equal the electric field E, we get Maxwell's first equation, telling us that the outward field lines emanate from an enclosed charge, or charge density. And this is divided by the permittivity of free space. The differential form of Maxwell's first equation follows from Gauss's divergence theorem. When there is no electric charge, there is no electric field divergence. And in the presence of an electric charge, field lines accumulate and pile up. Charges act like sources or sinks for the electric field lines. When a vector field exhibits the feature that its divergence is zero, we say that the field is solenoidal, which means that it oscillates back and forth as a field. But that also means that this oscillating effect is induced by something. But by what? When we observe the behavior of magnets and the magnetic field B, we observe that its divergence is zero. What does this statement imply? Well, it implies, one, that there are no magnetic charges or no magnetic monopoles. It says that the magnetic field is produced by something making it oscillate in time. And that the magnetic field lines can never pile up or accumulate. And that the closed surface integral, given by the divergence theorem, is zero, which is Maxwell's second law. Magnetic field lines form closed loops, and there are no magnetic monopoles. This is Maxwell's second law. A changing magnetic field induces an electromotive force. This is Faraday's law of induction, which states that an electric field path integral over a closed loop is related to the magnetic force induced by an electric field. It uses Stokes' theorem of circulation, since the E field, the electric field, is circulating around a closed wire, a closed loop. So, the electromotive force is the work done by the electromagnetic field in carrying a unit charge around a closed loop of wire. Now, according to Faraday, electromagnetic force is induced in a closed loop by the negative rate of change of the magnetic flux. And recall that that is given by the negative time derivative of the B field integrated over a surface. Thus we can make a connection that the closed path integral of the electric field around our closed loop of wire is the circulation of the E field, and that produces a change in the magnetic field. That change in magnetic field is exactly what Stokes' theorem describes as what happens when you circulate the electric field. Maxwell's third equation. This brings us to Stokes' theorem for magnetic fields. The closed-loop integral of the B field is equal to the surface integral of the curl of the B field over the surface. The fundamental property of magnetic fields is that, unlike electric fields, magnetic fields are not conservative. Recall that a conservative field is one that does the same amount of work on a particle moving between two different points, regardless of the path chosen. Magnetic fields do not have such a property. Instead, there's a relationship between the magnetic field and its source, the electric current. Ampère deduced that the closed-loop integral of the magnetic field is equal to the current enclosed in the loop multiplied by the permeability of free space. And Ampère's law is a statement that an electric current will result in a field with a magnetic magnitude proportional to the current. That is, if we take this integral, this line integral around the closed loop, it is the same as asking what is the circulation of this magnetic field over the surface. So this closed loop integral, this closed looped path integral, equal to the current enclosed multiplied by a constant, is also equal to the circulation around the surface. We can write the enclosed current as the integral of a current density capital J over the surface defined by the loop. Therefore, the enclosed current is equal to the surface integral of the current density over the surface area. And relating that to the magnetic field, we get the following situation. So now Ampère's law for an electric current states that the curl of B is equal to mu naught times J. But since the divergence of a curl is 0, this is only true for steady or constant currents. But this does not work for a changing current. For time-varying currents or non-steady currents, Ampère's law just doesn't apply. And this is where Maxwell steps in. Maxwell will make a correction to Ampère's law that will help unify all of the equations that are now known under Maxwell's name. Now, Maxwell proposed that a changing electric field induces a magnetic field. In particular, he said that the curl of the magnetic field is not just a constant times the current density, but also a constant times the change in the electric field. And this fixes the divergence problem and what Maxwell would call the displacement fixes Ampere's law. So from Gauss's law, we have the charge density over the permittivity of free space as the divergence of E. And since our particular current displacement, or current density displacement, given by Maxwell here is added on to Ampere's law, altogether the change to Ampere's law was just the last step in unifying the field of electricity and the field of magnetism into the field of electromagnetism. And the laws that unified by Maxwell have a profound conclusion. You see, it predicts the existence of electromagnetic waves. It also predicts that EM waves can propagate through free space, that the speed of an electromagnetic wave is the speed of light, and that light itself is an electromagnetic wave propagating through space. Further, electromagnetism is a radiation spectrum, and electromagnetism is what led Einstein to the photoelectric effect, his special and general theories of relativity. Maxwell was truly a giant in the theory of electromagnetism. We owe a debt of gratitude to Maxwell, for this video would not be possible without him. Thanks for watching. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.